Here we're being asked to find the amount S spent on advertising that maximize the profit for this profit function here, and also to find the point of diminishing returns. So we're trying to find S, the amount that maximize profit. So if we have a profit function, we know that maximizing it, or the point where it's maximized, occurs at our critical point. Our critical point occurs where our first derivative is equal to 0, or where it's undefined. So if we take our first derivative of this, we get negative 6s plus 70s minus 100. If we set this to equal to 0 and we solve it, first we could factor out negative 2, which leaves us with 3s plus 35s minus 50. Well, plus 50 here, and the minus here, since we factored a negative, is equal to 0. We proceed to factor, and this should be a square here. If we proceed to factor this, then we have negative 2 times 3s. This should be s equal to 0. And we have 10 here and 5. 5 times 10 is 50. 30, so this should be a negative and a negative, so that when we do multiply them, we get positive 50. So this is us factoring a trinomial. Doesn't matter how you factor it, but in the end, we should get negative 2 times 3s minus 5 and s minus 10. So then both of these equal to 0. S is equal to 5 over 3 or 10. So here we have two critical points. We're trying to find the one that maximizes it. So we can either do our first derivative test, or we can do our second derivative test. Second derivative test is generally a little less steps, so if we take our second derivative of this, we get negative 12s plus 70. Now if we substitute 5/3 for this, so I'll get p double prime of 5/3. This becomes negative 12 times 5/3, which will give us negative 20, which this will give us 50. Now, since this is a positive number, we know that when it's a positive number, it's concave down, and it's a minimum. So we're not interested in the 5/3 here, because we're interested in the value or the amount that produces the max. So let's try the 10. Now we're going to find p double prime of 10. So this becomes negative 12 times 10 plus 70, which gives us negative 50. Now because this is negative, we know from our second derivative test that when this is negative, it's concave up, which produces a maximum. So here, the number of units that will produce, that we need to spend, or the amount S that we're going to spend on advertising would be 10. And this could be 10,000, 10 million, whatever our units are being measured in. So here S is being equal to 10. Now, there's a second part to this question. It says find the point of diminishing returns. Now the point of diminishing return is where the second derivative is equal to 0. We already have our second derivative. So if we take our second derivative, which is negative 12s plus 70, and set it equal to 0, we get S is equal to 70 over 12, which reduces to 35 over 6. So the point of diminishing return, which is our point of inflection, or where concavity change from concave up to concave down, or concave down to concave up, same thing as the point of diminishing return, is where the dollars amount spent is 35 over 6. So in this example, we're told that a wholesaler sold a product for $40 per unit, and then the sales were 300 units per week. When this wholesaler increased the price to $45 per unit, sales went down to $275 per week. We're told that there is a linear demand function between the cost of the unit and the number of units sold. We're also asked to find what price per unit yield the maximum total revenue. So since we're trying to find maximum total revenue, we need to find the derivative of the revenue function. First, we have to derive an equation for our revenue. So since we're given 2 points, which are 40 and 300, and 45 and 275, we can find our slope since this is a linear function. You know, m would be equal to y2 minus y1, so it's 275 minus 300 over 45 minus 40. So this ends up being negative 25 over 5 or negative 5. So our slope here is a negative 5. We can then use our linear equation, the point slope form, to write an equation for our demand function. So we know that x minus 300 is going to be equal to our slope, negative 5, times p minus 40. So this is coming from our point slope equation. y2 minus y minus y1 is equal to m times x minus x1. So to find our linear equation, if we simplify this, we have x minus 300 is equal to negative 5p plus 200. And if you add 300 to both sides, x ends up being negative 5p plus 500. We know our revenue is equal to x times p. Now, since we're trying to find the price per unit that yields the maximum total revenue, we want to rewrite our revenue function in terms of p. So we're going to substitute for x. We know x is equal to negative 5p plus 500, and we're going to times that by p. So our revenue then is going to be equal to negative 5p squared plus 500p. Now, if they were asking us the number of units that would yield the maximum total revenue, then we would write our equation in terms of x. But here we're asking the price per unit, so we want to rewrite our equation in terms of p. So we know the maximum occurs where our first derivative, so we're going to have r prime is going to be equal to negative 10p plus 500. We know this occurs where this is equal to 0, so negative 10p plus 500 is equal to 0, or p is equal to 50. So the price per unit that will yield the maximum revenue is actually $50 per unit. Now let's get a price elasticity of demand. The price elasticity of demand is defined as the rate of change of demand divided by the rate of change in price. Now the rate of change of demand, the change in demand is dx over x, and the rate of change in price is dp over p. Now, by manipulating this, we get p divided by x all over dp by dx. So our price elasticity of demand simply becomes p divided by x all over dp by dx. Now this price elasticity of demand is abbreviated with this Greek letter eta. So eta is equal to p divided by x all over dp by dx. Now when the absolute value of eta is greater than 1, we defined our elasticity as being elastic. What do we mean by elastic? This means that a change in price will affect our change in demand. So if the price go down, this might means an increase in demand, or if the price go up, this might means a reduction in demand. So that's an elastic demand. When the absolute value of our elasticity is less than 1, then our demand is inelastic. Simply meaning that a change in price does not necessarily affect our change in demand. For example, gasoline. The price of gas go off, we generally tend to buy the same amount of gas we previously bought before. Or some tobacco products or alcohol. Here, if this price here goes down, then we might actually increase our consumption or buy more. So that's elastic. And inelastic, a change in price does not affect a change in demand. Now let's look at a couple of examples. So in this example, we're being asked to find the price elasticity of the demand function at this indicated value. We are also asked is to find out, is the demand elastic, inelastic, or of unit elasticity. You can recall that it's elastic when the absolute value of eta is greater than 1. It's inelastic when the absolute value of eta is less than 1. And it's of unit elasticity when the absolute value of eta is equal to 1. You can recall that eta is equal to P over X divided by dP by dx. Now dP by dx we can find from here by taking the first derivative. The first derivative of this would be -3. So if we replace P, which is 400 minus 3x, which is our P, divided by x. So this is P divided by x all over dP by dx. dP by dx is -3. So here is our equation for eta. Now at this indicated value, x is equal to 20, we have 400 minus 3 times 20 divided by 20 all over -3. So 3 times 20 would be 60. 400 minus 60 would be 340. 340 divided by 20 would be 17. So this ends up being 17 over -3. So eta is equal to 17 over -3, or -17.3. Now the absolute value of eta would be equal to the absolute value of this, which is 17 over 3. And this is approximately equal to 5 point something. Now, since this is greater than 1, we know that our elasticity is actually elastic, since the absolute value of eta is greater than 1. So this is an example where the price elasticity is actually elastic, which means that a change in price will definitely affect a change in demand.